Hello, welcome everyone, welcome back to my channel. Today we are starting our physics topic, which is a space. But before that, I'm running GCSE classes at just £6 per hour, and if you need any class for any subject from year 1 to A levels, just drop us an email at exactacademy@gmail.com. Classes are pretty affordable and given by the highly experienced tutors. So let me start with the space topic. Well, in space topic, the first thing that we'll be studying is about the objects of the space, basically, or about solar systems and the celestial bodies, satellites, artificial, natural. We'll be studying, that's the first thing that we have to study. But instead of that, I'm starting with the sun, the life cycle of the sun. And why is it so? Because it's very important. So obviously in the next lecture I'll be dedicating it to the solar system, but today we are studying about the sun, and obviously this is a part of the solar system and any star system. Sun is very important thing, but we are starting with this life cycle of sun, not particularly our sun. It's about all the types of sun, or you can say star more specifically. So we are dedicating this lecture to life cycle of a star. If I have to start with the basic definition of a star, it's just a burning ball, right? A big ball of fire, and which liberates heat. We receive that heat, we receive that energy from our sun, and definitely we are converting its energy as well. We are taking help from its energy to convert it into electricity and other works. Well, here we are studying about the stars, all the types of stars, like the small, bigger one, all the types of star. And this is the basic definition of a star that I can say is just the burning ball. And the first stage of a life cycle of a star, how it forms, we'll be studying from that part. And here you can see this picture is actually a picture of a nebula. Nebula is actually a very dense cloud of dust and gas. Like in space, dust and gas are scattered everywhere. Maybe they are the outproduct of, you can say, a dead star, that is a supernova star, or there can be so many reasons that there is a whole cloud. They are scattered. If I'm talking about the dust and the gas, they are all scattered throughout it. But a little friction in space can cause them all to come together and start sticking together. When they start to come together, obviously they start to form more dense cloud. When something comes closer to each other, obviously the density will increase. If the molecules are coming closer to each other, the density will increase, and that results in forming a very dense cloud. And that dense cloud, well, it's luminous. Now the question is, why this dense cloud is luminous? The reason being is nebulas are luminous because they emit or reflect light. And on the basis of that, they are actually categorized as emission nebula or the reflection nebula. Well, if I talk about the emission nebula, they actually glow due to the ionized gases. Now we know the ionization. Ionization is the process of forming the ions. So this glow is due to the ionized gases that usually these gases are hydrogen. So when a very high energy ultraviolet ray from any nearby star ionizes the gas, obviously a very high energetic you can say a source is required to ionize, and this is done by the ultraviolet rays. They actually ionizes the gas, and the electrons recombine with the protons, and they release the energy in the form of a visible light. Well, this here you can see is right this pinkish color, and this is because of the emission of the hydrogen basically. Well, the second type of nebula is called the reflection nebula. Well, they don't emit the light. Unlike the emission nebula, they don't emit the light, they don't have their own light, but they actually reflect the light from the nearby star. Well, Generally, the color of reflection nebula is bluish kind of, and that's because the blue light scatters more effectively as compared to the red light. Well, there is a third kind of nebula also, that's called planetary nebula, or they are actually this is actually the planetary nebula is more specifically I can say is it happens in a dying star, but as of now we are specifically talking about a nebula, a cloud of dust and gas, and they get their light because of being reflected or being emitted. Okay, go moving on to the next one. Well, a protostar. A protostar is the next stage of the life cycle of a star. This one, the figure here you can see is actually a protostar. Now, what happens in a protostar? Because we have seen in the first stage in nebula, it's actually a dense cloud of dust and gas. So, in this region, these you can say the molecular cloud starts to collapse under its own gravity, because obviously the mass has been accumulated, and where there is a mass there will be the gravity, and because of that they start to collapse under their own gravity. As the gas and the dust compresses, the core heats up. The important part is the nuclear fusion hasn't started yet. Well, the surface temperature, if I talk about the protostar's surface temperature, it is generally in the range of 4000 to 6000 Kelvin, and which actually liberates the yellow or orange light. Also, the surrounding dust in the collapsing cloud can retain the light and making it to look like more yellowish or orangish in color. Well, since in this process or in this protostar fusion hasn't begun, so it's not as hot, or you can say or as blue as the main sequence star, and the light is mostly due to the gravitational energy being converted into heat as the protostar contracts. Well, this phase lasts tens of thousands to few million years depending on the star's final mass. And when the core temperature reaches about, you can say 10 million Kelvin, it's a very high temperature, the nuclear fusion starts. And at this point, the protostar becomes a main sequence star. So the next stage is definitely the main sequence star, and let me see how a protostar changes into a main sequence star. This is the main sequence star. Our sun is in a phase of a main sequence star. So basically a main sequence star is a star that is the longest and the most stable phase of its life, in which it fuses hydrogen into helium in its core. And this process is called nuclear fusion, when the lighter elements fuses together to form the heavier element. When the nuclear fusion releases this kind of nuclear, because nuclear fusion or fission, these type of nuclear reactions produces a very high amount of energy, and the nuclear fusion inside the star releases the energy which creates an outward pressure that balances the inward pull of the gravity. So basically there are two types of forces being acted on this. The one that is the inside force because of the gravity, because gravity is always inwards, and the another one is the outward pressure or outward force basically given by the star because of the nuclear fusion that is happening at the core. And when these two forces are balanced out, and then this star becomes a most stable star, which we call as main sequence stars. So we can say that when these two pressure or forces are balanced, this star is in its most stable phase, which is a main sequence star. When now we know that it has transit from the protostar to main sequence star. So let me see how this transition happens. So the first thing is the gravitational contraction. The protostar continues to contract under its own gravity, and as it contracts, the core becomes hotter and hotter and denser. And once the core temperature reaches to, which I just told you, that the 10 million Kelvin, it becomes hot enough that the hydrogen nuclei starts to fuse together into helium. And then the fusion reaction takes place. So now let me see how exactly the nuclear fusion takes place. Why at lower temperature and pressure fusion doesn't take place, but at higher temperature it does. Now see, at normal temperature and pressure, the collision takes place. That means molecules come closer to each other and then they move away from each other. That's the simple collision. And the collision are perfectly elastic collision. That means there will be no loss of energy, loss of kinetic energy. We assume it to be a perfectly elastic collision, and they just come closer to each other and move away from each other just after touching. That happens in the regular collision. But when the temperature rises enough, that's the reason the high temperature and pressure are required for the fusion. It doesn't happen at any temperature. A very high temperature is required. Why? Because at such high temperature, hydrogen atom moves extremely fast. Obviously the temperature will increase their energy, and so does the kinetic energy increases, and so does their speed increases, and then they starts to move extremely fast. Their electrons are stripped away, leaving just protons. That means just nuclei. Now the fast moving protons just overcome their natural repulsion, because we know that if electrons are now away, they are only left with a positive charge, and we know that the same charges always repel. So this fast moving protons can overcome their natural repulsion, and then they fuses together. Also, apart from the high temperature, the high pressure plays a very important role. The star's own gravity squeezes the core material very tightly, and this actually increases the density, forcing these nuclei to come closer together. A high pressure actually keeps them compact, and it raises the chances of collision. And thus, because of that, when they just overcome that repulsion, they actually finally fuses together, and this fusion of the nuclei, or fusion of the lighter elements to form the heavier element, is called fusion. And that's why the fusion reaction happens in main sequence star. And by burning these successively, continuously, it produces a very high amount of energy. Well, these are basically the life cycle of these few stages are common in the life cycle of any star, but the later part changes the life cycle depending on the mass of the star. Whether the mass is more, that means whether the star is heavier or lighter, that will change the later stage of a star. So let me study that. We can just quickly see this one that I explained, that the molecules come closer and they just move away, they bounces back. This happens at normal temperature pressure, not normal temperature, we can say at those temperature pressure which I explained as 10 million Kelvin. Below that it happens like this, but once it reaches to that temperature, when they come closer to each other because of high temperature pressure, they finally collide and instead form a whole heavier nucleus. Now moving on to the next one, that is the later stages of a star. Well, as I described, after the main sequence star, the life cycle changes, but in the main sequence also there will be a little difference. The first thing is, on left hand side and on right hand side you can see the difference, because there is a difference in masses of these sun or these stars. So when a star is 0.3 to 8 times the mass of our sun, or the solar mass is basically a unit of heaviness, basically, because just like we have kgs, centigrams, milligrams, similarly for the very heavy object, specifically for the stars that we use this unit that is called solar mass. Solar mass is actually the mass of a sun, so that's called 1 solar mass. So if I talk about those stars that are 0.3 times to 0.3 to 8 times the mass of our sun, enters in this stage which is on left hand side. Well, this is the same nebula that we have studied. This is the same protostar that we have studied. And then the main sequence star also are of two types. Basically, here the yellow dwarfs and there is blue supergiants. So it's basically, we can say the yellow dwarf or the blue supergiant. It's they both are main sequence star. Same thing is happening. That means the outward pressure is equal to inward pressure and the fusion is taking place, but it's all depending on the mass. Let me study only the one that are on left hand side, these ones. So this is the main sequence star. The first one that you can see is looking like our sun, because our sun is also a main sequence star and also called as yellow dwarf, because it's like comes under too small to medium size star. It's actually same thing, a main sequence star that fuses hydrogen into helium, and it appears yellow because of its surface temperature that is approximately 5500 degrees Celsius to 6000 degrees Celsius. Well, this phase lasts for about 10 billion years. And energy from the fusion creates outward pressure that balances gravity, keeping the star stable. After this main sequence start, the next stage which you can see here is this one, and this seems to be reddish, and that's why it got its name as red giant. Well, once the hydrogen in the core is used up, fusion stops in the core and it actually starts to contract, because we have studied there were two pressure, the outward pressure given by the fusion and inward pressure by the gravity. When the fusion reaction stopped, there will be no more outward pressure, and because of that it starts to contract under its gravity. The outer layer expands due to the heat from the shell around the core, where the hydrogen is still fusing. Now, important part is in the core it has a stop. The fusion stopped in the core, but like around the shell, around the core there's a shell, the hydrogen is still fusing, and because of that there will be the generation of heat and the outer layer starts to expand. The star becomes huge and cooler on the surface, and hence it becomes red in color. Well, in the red giant phase, the core may start fusing helium into carbon and oxygen, that means to more higher elements. And this phase is shorter, well, not that shorter, it is still 100 million years, but as compared to main sequence star, this life cycle is shorter. Moving on to the next one, which is the planetary nebula. Well, eventually this star cannot fuse the heavier elements, and because it lacks enough mass. The outer layers of the star are just blown away into the space by a very strong wind that we call as stellar winds. Well, these layers from the glowing shell of gas are called planetary nebula. Well, despite the name, it has nothing to do with the planets. It just looks like it, so they it got its name as planetary nebula. Well, still we know that the fusion has stopped, fusion is not happening now, and even the outer layers are blown away, but the central hot core remains and lights up the nebula. And after this, it enters to the next phase, which is called white dwarf. Well, after the planetary nebula just finally drifts away, only the core left, and this core is very hot. So this is a very hot core now remaining, and this is called the white dwarf, a very dense, a hot object and equals to the size of the earth. You can see that it was once a very bigger star, obviously, which is like it can be between 0.3 to 8 times the sun, and now it has just become equal to the size of the earth, because it's just a core remaining. Obviously no more fusion is happening, and it glows because that leftover heat that was once there because of the fusion. Then it cools slowly over the next few billion years. Well, if I talk about the mass, its mass is just about half the sun's mass because it's very smaller, though it's very smaller in size, but it's very, very dense, and everything is now packed inside that smaller size, and still it's half the size of the star, half in the mass of the star. The next you can see here is a black dwarf. Let me tell you, black dwarf is just a theoretical thing. It's just a hypothetical object. It's what a white dwarf would become after it cools completely and stops emitting light and heat entirely. Well, the universe isn't enough old for any black dwarf, and that's why we're not sure whether they are existing or not, or there can be that stage or not. But as per the scientists, obviously, what will happen when it will lose all of its heat and when it finally become cold, dark, and dead? So the remaining part is called black dwarf, and this is the reason it's just an hypothetical object. So this is about the life cycle of the sun-like star. So I can just simply summarize it. It goes through after the nebula and protostar, it enters to yellow dwarf, which is main sequence, then red giant, then planetary nebula, then white dwarf, and finally to the black dwarf, which is actually a hypothetical. Now let me see to the other life cycle, to those that are greater than 8 solar masses, or you can say that are greater than 8 times the sun. I'm talking about those stars that are greater than 8 solar masses, and it goes till 50 solar masses. That means 50 times the mass of our star, of our sun. Well, this one is just like the yellow dwarf was a main sequence star that are low to intermediate mass having. This one is the blue giant, and they are very massive and hot star that are a main sequence star. They simply do the same thing, that means they burn hydrogen and convert it into helium. Well, this blue-white color is due to their surface temperature, which is very high, more than the twice the surface temperature of our sun. It has a temperature of more than 10,000 Kelvin, and because of that very high temperature, it gets its color, which is bluish white. Then mass is actually just like I described it, somewhere 8 to 50 times the sun's mass. If I talk about the lifespan, it is very short as compared to the smaller stars. As I told you, for smaller stars like our sun, it will remain in its main sequence stage for billions of years, but its lifespan is comparatively shorter and it lasts only for a few million years. Well, they eventually run out of the hydrogen and it starts to fuse heavier elements. And then it enters into the next stage, which is actually red supergiant. Well, after the core hydrogen is exhausted, the massive star expands into the red supergiant. Outer layers expand and cool, giving the star a reddish appearance, but they are still extremely luminous because of its size, you can say, or you can say about because of the temperature. Well, the fusion in the core will continue to form the heavier elements from helium to carbon to oxygen and up to iron. The iron core is the end point because iron doesn't release energy when fused, right? This is important. The fusion can take place only if the atoms keeps on fusing, liberating energy and forms a heavier element. But iron is the last point because iron doesn't release energy when fused, and it actually absorbs energy, leading it to instability. So that is the end of the supergiant. This is actually the bigger one. It happens the same thing because it's heavier in size, mass, and greater in size. This is called red supergiant. The next life cycle of a red supergiant is a supernova. As I told you that in red supergiant, the end point is the iron, the formation of iron. So once the core builds up too much of the iron, it collapses under its own gravity because of its heavier mass. And also the fusion is not happening, no more fusion is happening. So this collapse triggers a massive explosion that's called supernova. And in seconds, like within the seconds, the outer layers are blasted into space, and it produces a very intense light that it can outshine a whole galaxy. And heavy elements, that means the cold uranium created during this explosion. Important point is the heavier elements are created during the explosion, not in the red supergiant. The maximum or the end point is the iron. That was the heaviest element that forms inside the star. But during the explosion, further more heavier elements are formed and being distributed throughout the universe. And the elements that are now in your blood, in your body, my body, were once formed inside the star and like being distributed during the supernova explosion. The next is the two types of star. Again, the supernova will enter into either neutron star stage or the black hole stage, and it all depends on the masses. Well, if the core remnant after the supernova, because the explosion has blown away all the shell and everything, only the core will remain. And if this remnant core is between 1.5 to 3 solar masses, it becomes a neutron star. Well, neutron star, why it's called neutron? Because it's made of entirely neutrons and they are packed incredibly dense. The size is about 20 kilometers in diameter, but they are extremely massive. The star, you can see the size is not too much, but it's pretty massive. Gravity is enormous because gravity is directly proportional to the mass. The heavier the mass, more will be the gravity. And in this case, obviously it's enormous and the rotation can be very fast. Some neutrons emit radio waves as they spin, and they are called pulsars. The second one here, this one is called black hole. Well, if the core is more than 3 times the sun's mass, the gravity becomes so strong that even the light cannot escape, and it collapses into a black hole, a point of infinite density, and that's called a singularity surrounded by event horizon. Well, this is very massive object, and even the light cannot escape through it, so detection of the black holes are very difficult. So they detected indirectly through the gravitational effects on the nearby stars or the light. So this is basically about the life cycle of those stars that are greater than the 8 solar masses. They reach still 50 solar masses. Now let me see our summary table. So you can see here the blue giant, which is a massive, hot, short-lived main sequence star. Then it enters in a red supergiant, which is the expanded, cooler phase before the death of a massive star. Then it's supernova, which is a catastrophic explosion at the end of the massive star's life. Then it's a neutron star, which is a collapsed core of a supernova if the mass is a moderate, which is 1.4 times to 3 times. And black hole is the final remnant of the most massive star, where the core remnant is 3 times the sun's mass, or greater than the 3 times the sun's mass. So this is about the life cycle of a star, and if you have any doubt you can comment below and I'll definitely answer you. And if you need classes, if you want to book free online classes, or if you want to book for free demo, just email us at exactacademy@gmail.com. And also we are running the test series as well, and we have the mock papers as well. If you want to purchase mock papers, if you want to enroll yourself for test series, just email us at exactacademy@gmail.com. So that's it for today. Thank you everyone. Take care.